Okay, good afternoon, everyone. Thank you for tuning in for our online lectures. We will start now by going back to the magnetic field equation that we derived for the finite length of a wire. If you recall, this was the magnitude of the magnetic field we derived for a finite wire, while the y variable was sweeping from minus a to positive a, which means that the length was 2a. So a here is half the length of the wire. Now, here was the magnitude, and we said that the direction for the magnetic field is usually perpendicular on the plane that has the vector r and the differential element dl. So if I am to assume that this is x-axis and this is the y-axis as well, this way z would be out of the screen, then I can look at x here. If I am to look at this circle surrounding the wire, then here it is x. Here would be the radius r, right? But when this radius is aligned on the x-axis, then this r can be x, which is a special case in this case. Now, what is the direction of the magnetic field for this one? B will be this magnitude. We call this magnitude times the unit vector that is normal. If I am to look at this point, then the normal unit vector would be along what? Along the positive y. It will be along the positive y. Now, if let me be more clear here. If I'm to uh, if I take this one as the z, so let me delete this, and so if I take the upper one is z and y is in this case, so this is x. I guess this is clearer. This is y. So this is x, this is y. In this case, the normal unit vector here will be in this direction, which is basically normal to the x and z plane and parallel to y. So this one would be j hat. So I am talking here, this is going to be j hat. So it depends on how much is this radius. The radius is the general case, which means that at any point it will be tangential. If I am to look at this point based on the direction of the current going up, then this one is the tangential. This point, this one is the tangential. Notice that when the current is going up along the positive z axis, then the magnetic field is counterclockwise. At every single point, this counterclockwise means a tangential component, and it is perpendicular on this radius. Now, when it comes to here, this becomes a special case. When the point sits on the x-axis, this becomes a special case. At this point, r will be the same as x. Now, Look what's going to happen if my point of interest is sitting on the y-axis. It will be tangential. The magnetic field will be tangential. In this case, guess what is the direction of the magnetic field for this one? It will be minus I hat. So because the direction is always perpendicular, whatever the point is, it will the normal unit vector or the direction of the magnetic field will depend on where is that point. Where is that point? The special case we have is when this point is sitting on the x-axis, in this case counterclockwise, means direction is going along the positive j. If this point now is on the y-axis, then the counterclockwise means that the direction is minus I. No, I made it Z. I made it Z. I made the upward Z and I made this one to be Y and this one to be X for clarity. So I made the current, I made the current going Z up, X and Y. Z up, X and Y. Let's look at it this way. In this case, in this case, I have the magnetic field depends on the location. Where is the point of interest? If the point of interest is this one, then based on the current moving up, the counterclockwise means the magnetic field is in the positive J. If the point is here on the y-axis, positive y-axis, this means that the unit vector is minus I. If the point is here, if the point is here on the x-axis negative counterclockwise, this means the direction of the magnetic field will be pointing this way. Oh, let me fix this one. Will be minus J. If it's here along on the y-axis, negative y-axis, it will be plus I, and so on. So it depends on where is that point that you would like to calculate the magnetic field. The direction of the magnetic field will always be perpendicular on the plane that has the displacement vector and the differential element. We'll see this more in the coming examples. So let's look here at this case where, as you can see, the current is going in this direction. The current is going in this direction. This means if I take my thumb in the direction of the current, it will be curling, as you can see, in this direction, in that direction. So I can look at this point. See this point? The magnetic field is perpendicular. Or see this point? Magnetic field is perpendicular. Or that point, magnetic field is also perpendicular and tangential to that circle. Now the common between the circle is all of them are at the same distance. So all of them are at radius r. Okay, now let's extend the equation that we found for an infinite wire. In this case, we will be substituting the, if you recall, the magnetic field that we found for a finite wire of a length of 2a was a over a squared plus x squared, or I can say r if I replace this x with the radius. Basically, that's the radius. Now, if I substitute alpha with infinity instead of integrating from minus a to plus a, I'll be integrating from minus infinity to plus infinity. This means I can substitute this alpha with infinity and this one with also infinity, which means that whatever the value of the x will be way smaller than the infinity, and this will end up to be infinity over infinity equals 1. And now the magnetic field will be simplified down to B equals to mu naught I divided by 2 pi r. R is the radius, as I said earlier. R is the radius of the circle that this point of interest is sitting on. So this now is the magnetic field. Again, this is magnitude. If you want to find the direction is always theta hat. The direction is always theta hat. This is number 13, L13. It's already on the course link. Okay, so this is the magnetic field due to the infinite wire. Always remember that the right-hand rule is always applied to find the direction of the magnetic field. Now, let's solve this problem. We have here two hikers are reading a compass under an overhead transmission line. So we have a transmission line. We have a transmission line, a wire, an infinite wire, uh, carries a current of 800 ampere uh, at, a, at a height of 5.5 meter above the ground. The current flows in the horizontal direction parallel to the ground from north to south. Find what is the magnitude and direction of the magnetic field due to the wire on the ground directly under the transmission line. So if I am to, if you open the slides, if you not have the question in front of you, open your slides. I will draw the problem based on my understanding. So here I have my coordinates are x, y, z. So I will take this wire as sitting on here parallel to my y. Now y and x are the plane of the ground. I will put my wire right here such that it is 5.5 meter. The height is 5.5 meter. And I have my north going this way, which means my current now is going in this direction from north to south. My current is 800 ampere. I need to calculate the magnetic field and the direction right below, which means right on here on the y-axis, right below, which means right on the y-axis. Any point on the y-axis should be enough to take as the point of interest to calculate the magnetic field, because this will be the point that is 5.5 below the 5.5 below the wire, and it will be right below, it will be sitting on the y-axis. So any point here should be okay. So if I want to calculate the magnetic field, I need to put my magnetic field equation. Magnetic field here equals to, for the infinite wire, is mu naught I divided by 2 pi r. We said r is the radius, and right now this radius is 5.5 meter. Any point that is 5.5 is the radius, and right now this point is sitting on the z. So the z here is 5.5. So my r here can be on along the z axis. Now the current, as I said, as this is the magnitude, r magnitude, which is 5.5, and I have my current here going into the negative j direction. We'll leave this for the direction for the time being, and we'll calculate now the magnetic field magnitude, which equals to 4 pi 10 to the power minus 7 times 800 magnitude divided by 2 pi times 5.5 meter magnitude, and the answer is B magnitude equals to 2.910 to the power minus 5 Tesla. Okay, so I found the magnitude of the magnetic field. What is the direction of the magnetic field? The direction of the magnetic field, if you look at the current that's going in the negative y, and you curl your fingers right here, you will find that the magnetic field will be going in this direction due to the wire. The magnetic field due to the wire where did the value of u, what u? Mu, this is the permeability of the free space. It's a constant. Mu, it's a mu naught for the free space. 4 pi 10 to the power minus 7. Again, using the right hand rule, your thumb is pointing toward the current, in the direction of the current, and your fingers will be going, curling in the direction of the magnetic field. So in this case, if I take, this is my current going into this direction. So if you curl your fingers, you will see that right at this point, the magnetic field is pointing in the positive x axis. Again, you need to look at the direction of the current. You curl your fingers. You look at the point of your interest to find out what is the direction of the magnetic field. It will always be perpendicular. So if you take this as R, it will always be perpendicular. So this is your R, which is the Z right now. It will always be perpendicular on the plane that has the differential element and the vector. And the vector here, as you can see, my R here is minus Z 5.5. I'm using here the magnitude. Okay, so in this case, my magnetic field for the wire is, again, this is the wire. This is the wire. Magnetic field for the wire is 2.9 with the direction times 10 to the power minus 5. This is going to be I hat Tesla. Okay, so we found the magnetic field due to the wire right below the wire, right below the wire. And then he gave me the magnetic field of the Earth, and he said it's pointing north. So the magnetic field for the Earth right at this point is pointing north. My north is along the positive Y, so this is the magnetic field due to the Earth. So I have two vectors, which means the magnetic field, the net magnetic field will be B net magnitude will be B wire magnitude squared plus B earth B net magnitude as 2.9 minus 5 squared plus 0.5 or minus 4 squared B net magnitude equals to 5.7 10 to the power minus 5 Tesla. And the direction is, if you go to here, you will see if I am to take, if I am to look from the top, if I am to look from the top, this is what I will be seeing. This is B wire, and this is B earth, and then the net will be this, and this is theta, the angle. So theta is tan inverse of B earth divided by B wire magnitude, which means theta is 60 degrees. BE is the magnetic field of the Earth. If you open your slides and read the question, the magnetic field of the Earth was given to me in the north direction. Okay. So this is how we calculated the total magnetic field due to the superposition of the magnetic field generated by the wire that, as you can see, was going along the x-axis, and the magnetic field of the Earth that was going in the direction of the positive y-axis. Now remember, I decided on the coordinates to use, so this was left up to you to decide what is the direction of the north, what is the direction, where is this line is sitting. As long as it is sitting horizontal, that should be okay, which means parallel to the plane of the xy, which is the plane of the Earth. That should be okay. So you could have put the wire along the x-axis. You can have leave it as along the y-axis. It was up to you. The force, we were evaluating uh, the magnetic field. We will come later on to an example where one of them, F is I delta L I dl vector cross B vector. So you would be looking at a current and an external magnetic field in that case. We will come to a point where we generate the magnetic field from one wire and evaluate the effect of this magnetic field on a second wire that has a current. So we will come to that later on. This is the magnetic force. I dl cross B. B is an external magnetic field that we are evaluating its effect on a wire that has a current. So here, if you think about it, you have external magnetic field and you have another magnetic field that is generated due to this current going through that wire. We will come to this one later on. Where we evaluate a magnetic field on another wire that has current into it. Both wires are generating magnetic fields. One of them would be considered external, and the other one is the wire that is affected by this magnetic field generated from the second wire. We'll come to that later on. Okay. Now let's move to this question. In this question, we have, as you can see here, two wires that are parallel, and they are all in the same direction. So right now what we're seeing is only a cross section where those wires are parallel and they're going, and their current is going out of the screen. Their current is going out of the screen. We need to evaluate the magnetic field generated by both of them at point P. So they are infinite wires, they're very long wires. So in this case, we will be using the infinite wire equation, which is the magnetic field B magnitude equals to mu naught I over 2 pi r, where r is the radius of the circle that the point of interest of is on it. So right now, if I am to evaluate the magnetic field right at this point P due to this current, they're equal current in the same direction, but just to make sure that I understand, let me call this one wire A, and let me call this one wire B. Okay, that's good. So if I am to evaluate the magnetic field generated by the wire A, then based on the right hand rule, my you know current going out of the screen and the magnetic field will be counterclockwise. In this case, if magnetic field is counterclockwise, then the magnetic field will be pointing up right here. So this one is BA. Now, if I look at the magnetic field generated by the wire B, again, out of the screen, counterclockwise, but this time, since the point is at the left side, so notice when I say counterclockwise and the point is here, this means it's pointing downward. But what happens if the point is here, counterclockwise? Notice that in this case, the magnetic field will be. Okay, so back to the question where we said wire A is going to generate a magnetic field that is pointing upward. However, wire B, if we look at the direction of the current going out of the screen, curling counterclockwise, it will result into a magnetic field that is pointing downward. So this is going to be the magnetic field pointing downward, and in this case, the net magnetic field will be pointing upward. That's exactly the answer, yes, because we know that the magnetic field is inverse proportional to the distance. So right now I have here, let's say this is RA, and I have this one as RB, and RA is greater than RB, RB is greater than RA, which means the magnetic field due to the wire A would be greater than the magnetic field due to the wire B. This is how we calculate the magnetic field, and you can see that when you have two currents that are parallel and going in the same direction, any point in between, the magnetic field will be due to the subtract of one from another. So it will be destructive. There will always be subtracted in between. That's why at any point in between those wires, you will see that they will always be in the opposite direction if the currents have the same direction as we have here in this problem. Okay, now let's move on to the next question. In this question, we have the two wires that are equal in magnitude but opposite in direction. And in this case, we need to calculate that wire. So the distance between those two wires is up A. So the distance here between those two wires is 8 centimeter, and we have a net magnetic field that is pointing downward with a value of 1 × 10⁻⁻2 Tesla. Point P is 2 centimeter, and then this is going to result into point P being 6 centimeters away from wire number 2. Okay, so from what we have seen in the previous question, we've noticed that magnetic field, when both currents are parallel and then go and they fly in the same direction, we notice that the magnetic field in between will be the difference, will be destructive. Now here, since we have the currents are opposite in the direction, the magnetic field will always be constructive. They will always add in between. They will always add in between. That's why, if, for example, if we look at this example here, where I have both the currents that are opposite, we call this one I1 and this one I2. At any point in between, the current, the magnetic field due to I1 will be B1. Notice the right-hand rule, try the right-hand rule. However, for the magnetic field coming from I2, if you follow the same right-hand rule, you will notice that the magnetic field is also in the same direction. Why? Because both currents are opposite. It's going to result in always constructive. They will always add in between. So this is the point that this problem is built upon. Okay, now let's start with solving this problem. In this problem, as I said, we have the magnetic field. The coordinates are given to me, y, x, and here I have my wire 1, I1, and here I have my I2. Now, since the magnetic field at the point P here is pointing downward, so this is my B net. Since it's pointing downward, this means, and since they are opposite in the direction, this means they are constructive. This means they're being added. They add and they are constructive. This means both of them are pointing downward, which means the B1 coming from I1 is pointing downward, and the B2 coming from I2 is also pointing downward. So if I look at the magnetic field that is pointing downward due to the right hand, take my fingers and make my fingers to rotate such that the magnetic field is pointing downward, I can notice that the current in case I1 is into the screen, and the current in case I2 is out of the screen. Just by knowing that it is constructive, just by knowing that they will be added, just by knowing that both of them are supposed to be pointing downward, I figured out that I1 is entering into the screen and I2 is out of the screen. So now I know the direction. Now let's go back to continue solving. Let me start first with the B1. So I have B1 as follows, mu naught. I will put I1 as magnitude and take the sign of I1 and put it and give it to the unit vector. So here I have I1, my I1 based on this coordinates, I have X, Y, Z is pointing out of the screen, which means that the direction I1 is negative K hat, right? the direction for I1 is going into the negative k hat. So I1 is minus along the z-axis. I1 is minus. So if I put I1 as magnitude 2 pi, let me call this one R1, right? Now the direction of the magnetic field will be pointing based on this, it will be pointing minus j hat. So this minus j hat is basically, this minus came from the I, right? Because the I was pointing in the negative direction, I had my magnetic field here at this point pointing in the negative direction of the Y. So this is where the Y came from. Because if you take I1, if you assume that I1 was positive, it will give you a magnetic field that is pointing in the positive Y direction. But what made this magnetic field to flip and go in the negative Y direction is because the current is going through the negative direction of the Z axis. So this is how I write the magnetic field in terms of my current I1 magnitude. And now for B2, it is mu naught. I will write it as positive as well, over 2 pi R2. And now the direction for the magnetic field is also minus j hat. Now, we know that the sum of those two vectors is going to give me also a negative direction along the y-axis. So if I put B1 plus B2, I should be getting the 1 10 to the power minus 2 minus j hat as well. Substituting now my B1 with the mu naught I1 magnitude over 2 pi R1 minus j hat plus mu naught I2 magnitude over 2 pi R2 minus j hat equals to 1 10 to the power minus 2 minus j hat as well. Yes, they are magnitude wise are equal but opposite in the direction. Opposite in the direction. That's why I wrote them as magnitude. So magnitude wise they are equal. The direction wise is going to be interpreted as I said, I moved the sign to the unit vector. So the unit vector now is the one that is responsible for the sign of the unit vector. Basically, the minus here came from the minus here, and the B1 came from the current. The minus came from the current. However, here the current was positive, and the minus direction was the original direction of the magnetic field if the I was positive along the z-axis. So right now, if I am to substitute 4 pi times 10 to the power minus 7 over 2 pi times 2 centimeters I1 magnitude minus j hat plus 4 pi 10 to the power minus 7 over 2 pi times 6 centimeter minus j hat equals to 1 minus j hat. Now, as you can see, all of them are J hat. J hat will cancel. And I2 magnitude is the same as I1 magnitude. I substituted I2 magnitude with I1 magnitude. Pi will cancel. 4 will cancel. So I ended up here with 10 to the power minus 5 I1 plus pi 2 with 3 plus 1 over 3 10 to the power minus 5 I1 equals to 1 10 to the power minus 2 and I1 in this case is 750 ampere. Now here we're dealing with the infinite wire. In the infinite wire, we used this equation that basically mu I over 2 pi r and a normal unit vector on the plane of the displacement vector and the wire, the infinite wire. So here, as I said before, because the net magnetic field was pointing downward, this one has to be pointing downward. This one has to be, the magnetic field generated from this current has to be pointing downward. The magnetic field from this current has to be pointing downward as well. So they were adding, the magnetic fields were adding at this point. So both of them has to be pointing downward. So I knew the direction of the magnetic field from knowing the direction of the net magnetic field. And then I put down all the equations for field number 1, for field number 2. I equate them. I know that the magnitude of the first current equals the magnitude of the second current. That's why I replaced I2 magnitude with I1 magnitude. And then I worked out this equation. And there how we found the current. Currents going in the opposite direction parallel, this means there will be generated magnetic field in between that is constructive, period. Currents that are going in opposite directions will be generating a magnetic field that is being added. The magnetic field will add in between. Okay. Okay. So let's move on to the next question. In this question, we have a wire, as you can see, with a battery connected. There's a current. If the currents are in the opposite directions, then the magnetic field between will be constructive. If the currents were parallel and in the same direction, the magnetic field in between will be destructive. Okay, now back to this question. If I have this wire that has this current going through, and I would like to rank the deflection of my compass. I have a compass that I am putting right on top at those locations, P, Q, and R. I want to rank them in terms of how strong the compass will be deflected. So I will rank them in descending order, starting with the maximum deflection, medium deflection, and minimal deflection. Now, what happens if I put the compass right on top of the wire, right at point P? If you think about it, if you follow the direction of the wire, your thumb, then you will see that the magnetic field generated will be pointing downward based on the right hand rule, right on the top at point P, right on the top on point P, the magnetic field will be pointing downward. If I look at the point Q, I have two currents going in the same direction. Those two currents are going to result into magnetic field that is stronger than the P case, right? Why? Because now I have two wires. I have two currents. Each one of them is contributing to a magnetic field. So they will add, I end up with a stronger magnetic field right on the point Q. What about point R? I have a magnetic field. The current is going this way. I have, for the top one, I have the magnetic field pointing downward. For the bottom one, I have the magnetic field pointing upward. So I will end up with two equal magnetic fields that are canceling, and the magnetic field for R would be 0. So if I am now to order them in descending order, they should be QPR. Which one is the QPR? QPR is E. And the answer is E. I'm not looking at a point in between. I'm not looking at the point in between. This point is right on the top of both of them. So you can think as if you have the point as you're holding the compass right on the top. So right now, if you're holding the compass right on the top of those wires, it will not be in between. So that point will be on the top of both of them. And in this case, it will be, the magnetic field will be in the same direction. Okay. So let's move on to this question. In this question, we have two parallel wires that are 5 centimeters apart and carry currents as shown. One of them, the top one, is going to the right and the bottom one is going to the left, while I have two differential elements here of very small, tiny wires that each of them is 1.5 millimeter. So this one is 1.5 millimeter, and this one is 1.5 millimeter also at the same location. I need to calculate the magnetic field right at the point P due to this DL. I will be calling this one as a DL. I will be treating this one as if it's a differential element, very tiny wire. So how do you solve this problem? Okay, so those are my wires, my two wires. This is my point P, where I will put my coordinates. Okay, so those are the two parallel wires. I have one of them. I have one of them going in this direction. Current is going in this direction. I1, I'm going to call this one I1, 12 ampere. The current I2 is 24 ampere. I have my DL. I will call this one as DL1. This DL1, it's going along the x-axis, so it will be 1.5 millimeter I. This is the same for DL2. It will be 1.5 10 to the power minus 3 also I. We've said that we always take the differential element to be positive and we'll let the current decide on the direction. So this is what I did. Now I have here two vectors. This is I would call this one R2 and I would call this one R1. And both of them, they have the same magnitude, 8. So I have here R1 equals to R2 equals to 8 centimeters. So this little differential wire is going to give me a little differential magnetic field. So if I am now to put my major equation, this major equation would be dV1 equals to mu naught I1 divided by 4 pi. Notice I'm using here the differential equations, the main equations, dl1 plus r hat. I will put it right away as r1 vector over r1 cubed. Now we need to find r1. What is r1? R1 will be the summation of those two vectors. Let me put that in different color. R1 will be this vector plus this vector, and R2 will be this vector plus this vector. Now, this vector is the same for both, which is xi hat. This vector, this one, would be minus 2.5 or 2.5 centimeter, which is half the distance, and the direction is minus j hat. However, this one will be 2.5 minus 2 j hat, positive. So one of them is negative, the one that goes in the negative direction, and the other one is positive. That's it. So my R1, I will write the R1 in blue. R1 is xi hat minus 2.5 minus 2 j hat. However, R2 is also xi hat, but this time is plus 2.5 10 to the power minus 2 j hat. So I have now dl, the differential element, for both dl1 and dl2. I have the vector r1 and r2. I have the magnitude for r1 and for r2. I am ready to put everything together. Then dv1 would be 4 pi 10 to the power minus 7. I1 is What is I1? I1 is positive 12. So times 12 divided by 4 pi times DL1 is 1.5 10 to the power minus 3 I hat cross x I hat minus 2.5 10 to the power minus 2 j hat. Right? It's I hat. X I hat. It came from the vector R1. R1, this vector R1 equals the summation of this vector, which is X I hat, right? Minus in the positive direction, which is 2.5 centimeter minus j hat, minus j hat. Same for R2, but the y is plus j hat. Okay. Now, if you recall, doing a cross product between I hat and I hat is going to give you here 0. So dB1 equals to, if you work out the calculation here, paying attention that I hat cross minus j hat is going to give you minus k hat. So the magnetic field here will be 0.088 10 to the power minus 6 minus k hat Tesla. Now, if you do the same for dB2, minus 24 times 1.5 milli I hat cross x I hat plus 2.5 10 to the power minus 2 j. This is j. This is j. J hat divided by 4 pi. Yeah, here we forgot to divide it by the 8 centimeter cubed divided by 8 centimeter cubed. Again, I hat and I hat is going to be 0. However, I hat cross j hat is going to be k hat, and you have the minus here, then the direction would be minus k hat as well. dB2 magnitude will be, if you do the calculation, it will be 0.176 10 to the power minus 6. Direction is minus k hat, which is in the same direction of the dB1, and now the dB net is the summation of both, will be 0.176 minus k hat plus 0.088 10 to the power minus 6 minus k hat, and dB net equals to 0.267 10 to the power minus 6 minus k hat Tesla. Remember, the R1 vector is the summation of an x I hat. I don't know the distance here, and it's in positive direction. So it's an x I hat minus 2.5 or plus 2.5 minus j hat, because it's going into the negative direction of the y. So this is how we calculate the magnetic field right at that point. If you want, we can continue. If you want, we can stop. Okay. So do you have any questions? Shall we continue? Okay, I think I'll stop here. I will stop here, and we will continue in the next lecture.